Next, we're going to look at some network services. Let's start with Dynamic Host Configuration Protocol, DHCP. This service dynamically assigns IP addresses to DHCP client nodes on the network. Typically, you will statically assign IP addresses to your servers and infrastructure systems, and it's typically the client systems that are dynamically configured using DHCP. The next service we're going to look at is a name resolution service that maps the fully qualified domain name of the various nodes on the network to the IP address. So this provides name resolution services. Users are familiar with the friendly names of the nodes on the network like webserver1.boboville.com, but DNS system provides the IP address for that named system so that the IP network stack can accurately transmit the queries and responses back and forth to the appropriate systems. Next service down is X.500 or directory services. Now this is the network service that provides us a security structure. Objects within the Active Directory or within the directory services database are typically trusted objects, and objects outside this directory services database are untrusted. So this is a way that we can authenticate and authorize user access to resources on the corporate environment. This is typically a corporate level or an enterprise level service. The next service we see here on the list is for email distribution and storage. We'll start with the Simple Message Transfer Protocol, SMTP. SMTP protocol transmits email from client computers to the email servers and from email server to email server for email distribution. However, SMTP is not used for client retrieval of email. So SMTP is from client to server and from server to server email transmissions. For a client to download their email, they will typically use either POP3 or IMAP4. That's the Post Office Protocol version 3 or Internet Message Access Protocol IMAP4. Now these are client retrieval protocols for email, and this typically requires an email application, something like Microsoft's Outlook application. It's not uncommon that the email server will also provide a web-based access, but this uses a browser. So this is typically done over port 80 or the SSL equivalent 443 for the email retrieval if that retrieval is done over HTTP or HTTPS. Moving forward, we'll look at some other networking services such as file sharing services. Now on the enterprise network, we will typically provide repositories, server-side repositories for all of the enterprise's data files. We typically don't want these data files left on client workstations because very often these client workstations may get damaged. If they're laptops, they're traveling around, they may get lost or stolen. Typically, in the enterprise, we want central repositories for these data files so that we can easily facilitate and help to ensure successful backups of these in case of disaster recovery requirements. So we have LAN-based file sharing services. We also have internet-based file sharing services. Essentially, HTTP, the web protocol, hypertext transfer protocol, is for file sharing. It actually is a file distribution protocol. However, it builds into it on the client side a processing and presentation function as well. So it isn't just direct file sharing. A classic file sharing service for internet-based is the file transfer protocol, FTP. Now this is one of the original internet-based protocols for bulk file transmissions. And more we are moving towards cloud-based services for file sharing. In other words, we will have a cloud environment, perhaps private, perhaps public if we want to lease space on someone else's infrastructure. But we will use web-based services now for our file repository and then later file retrieval, file access. So this is cloud-based services, a relatively new component in our file sharing services. We also have the need to print very often. So In an enterprise environment, we don't necessarily want to buy a printer for each cubicle, each user. So we very often will have a printer pool, and users will share a printer. So we'll need to provide a printer server and then share those printing services to users. We have application sharing services, and these are typically client-server-based applications, such as the email services that we referred to earlier in this lesson. And the client-based component would be perhaps Microsoft's Outlook or some other application along these lines. So this is a typical client-server application sharing service where the client requires or desires the use of a particular service, and he actually has an application that is configured and specifically tuned towards that server's services. Now, something that we'll find very often in the enterprise, maybe not so often at home, is remote access of the networking environment. And this requires network access services. So these are typically for remote access. Because the users that use remote access are not within the physical confines of the facility, we have heightened concerns about authenticating these people more strongly. Because they don't have to walk past our security guard with a badge, they don't sit down in a cubicle in our office where the coworkers would recognize a stranger versus recognize that this is the authorized user for this environment. We need to more strongly authenticate these remote access users. So we'll typically use what we call a AAA service for authentication, authorization, and accounting. Today, that third A, accounting, is more often auditing or accountability. Back in the early days, this literally was a cha-ching kind of accounting where we're going to bill somebody a nickel for every kilobyte they upload or download. So these AAA services start with the remote authentication dial-in user service, terminal access controller services, and Diameter, the new generation of these AAA authentication services. We very often will have true dial-in services. Now, these would be using an analog modem over telephone lines. These were the original remote access servers, and it was truly dial-up using telephone lines. Now, that same service has evolved to include the virtual private network or VPN concentrator services. Wireless access points and controllers also will use these strong authentication services for remote access, and also an ancillary or support service for these remote access services is network access control to substantiate and validate the security health of these computers, these remote nodes that are trying to access our corporate enterprise. So typically we'll very often implement network access control to qualify the state of the security health of the remote accessing node, and if they aren't healthy enough, we remediate them to a specific LAN, isolate them on this LAN, and provide then services such as antivirus, patching for updates, things along these lines. So if there are any sort of security concerns, we let them remediate themselves once they get healthy enough that I can trust them on my corporate LAN. Perhaps then I will allow them to access resources after they've been strongly authenticated. And finally, a service that is commonly used on the enterprise network for strong authentication and security is certificate services based on X.509 digital certificates. So these are a handful of network services that help to support and substantiate the enterprise level computing environment. We'll take a break here and we'll pick up shortly. In this lesson, we're going to pick up with some more detailed analysis of some of these infrastructure components or services. Now, the first one we're going to look at is Dynamic Host Configuration Protocol, or DHCP. And again, this is used to dynamically assign IP address configuration details to DHCP client nodes on the enterprise network, typically enterprise network. This might also be used in the home as well, but the level we're talking about here, we're looking at an enterprise. Typically, your infrastructure systems like servers, routers, DNS, DHCP, these services will have a statically assigned IP address and other IP configuration details. This would be defined by the network administrators, and they would manually sit down at each of these systems and manually and statically configure these details. However, we might have, let's say, 100 servers. Well, those 100 servers might support 2,000 client computers. We don't want to have an administrator sit down at 2,000 different client computers and maintain these IP configurations on these systems. So what we'll do is we'll set up this infrastructure service called DHCP that will dynamically allocate IP address configuration details to these client machines. Now, as you see on the dialog on the right-hand side of this slide, this would be the IP version 4 configuration dialog in a Windows computer. And as you can see, this particular system is configured to be dynamically assigned IP information, including IP address, the subnet mask, the default gateway. That gateway, by the way, is the router that is local on this node's particular segment. And we also would dynamically assign the name resolution servers IP addresses here on this same dialog. So we could use the lower radio button to statically input each of these parameters if this were perhaps an infrastructure system. However, if it's a DHCP client, we'll use the upper radio buttons that says obtain an IP address automatically and obtain DNS server address automatically. That says this is a DHCP client. Now, DHCP is a broadcast-based service. In other words, when a client node boots up and loads its network stack, including IP version 4, the system will check to see if there is statically assigned IP parameters, such as IP address, subnet mask, default gateway, DNS, perhaps some other details as well. And if it is not statically assigned, then this client, this IP stack, recognizes that it must acquire this IP configuration information from somewhere. So it sends out a discover frame, a DHCP discover broadcast, and says, hey, if there's a DHCP server out there, please, I need an IP address. Now, if there is a DHCP server that hears that broadcast, in other words, it's within the same broadcast domain as the client that transmitted the request, the discover, the DHCP server will submit a DHCP offer. That's from the server back to the client, and it says, hey, client, I'm a DHCP server, and here's an IP address. Now, because of fault tolerance, we very often will configure in the enterprise multiple DHCP servers that can hear each DHCP broadcast. Just in case one of the servers is down, the other server can provide the IP configuration. So very often, multiple responses or offers will be provided in response to the DHCP discover. Now, the first offer that the client receives, that client will request that particular offer from that DHCP server. Why? Because that server was the first one to provide the offer. Therefore, I'm getting better service from him than from anybody else that's providing offers. The client will submit a request broadcast back to the DHCP server, and that same DHCP server will now reply with a broadcasted acknowledgement, DHCP ACK, or acknowledge. So our 4 frames are discover from client to server, offer from server back to client, request client back to server, and acknowledge server back to client. So it's a 4 broadcast process to acquire an IP address on a DHCP client. As we said, your infrastructure systems are typically statically assigned, and historically, DHCP is the 3rd generation. First, we had reverse address resolution protocol. This was the very initial way that client computers could acquire an IP configuration set of parameters. That evolved into something called the boot protocol, or boot P, and then finally DHCP. Now, as these protocols evolved over time, more and more services were built into them, more and more capability was built into them. So DHCP is the current 3rd generation of the dynamic assignment of IP configuration details for the clients. Now, the DHCP is not authenticated. In other words, any computer, good guy or bad guy, that can connect to your IP segment could acquire IP information and communicate with the DHCP server. So the concern here is, because it's unauthenticated and anybody can access this DHCP server, that makes the DHCP server fairly vulnerable. So there are a handful of attacks that are available in the DHCP protocol. Now, the first one is that a bad guy can stand up a DHCP server if he can plug into your segment. In other words, anybody who has either physical access to your wired infrastructure or perhaps access in your wireless infrastructure could stand up a DHCP server and provide bad information to these clients. In other words, this is a denial of service attack in this particular case because let's say the network is a 10.10.10.0/24 network. Well, the bad guy could set it up as 172.16.0.0/24 network, and the clients that use him for DHCP will not be able to connect to the enterprise. And again, remember, this is unauthenticated. It's all broadcast-based, and the client will request the offer from the first DHCP server that responds. He can't tell whether it's a good guy or a bad guy. So standing up a rogue DHCP server is one of the easiest attacks to accomplish. It's a way to implement a denial of service attack, or we might actually steer those clients towards the bad guy networking infrastructure in an attempt to try and steal sensitive information. So we're keeping the good guys away from the real legitimate services, and we might actually be able to steal sensitive information or perhaps inject malicious software into these client computers. Now, another attack on DHCP is a client computer can request 100 or 1,000 or 10,000 IP addresses. All he has to do is have the client node acquire an IP address for a certain period of time, and then that node would submit a new request for a new IP address using a different MAC address, and then make a request for a new IP address using a different MAC address. The DHCP server can't tell that these are all the same computer. He thinks he's just a very busy guy, that there are a lot of client nodes in need of IP addresses. And before too long, the bad guy who's acquiring all these IP addresses unnecessarily will deplete the available pool of IP addresses. Now, legitimate clients cannot acquire an IP address. Why? Because the bad guy has used them all up. So there aren't any more available IP addresses for legitimate clients. This is another denial of service attack. Now, in other lessons, we described the layer 2 device called the switch. And the switch today has replaced all the hubs and typically connect directly to each client node. Because we have a little bit of intelligence on this device, we now can apply an application to that device that can filter, and using an administrative console on many of these new enterprise level switches, we can implement something called DHCP snooping. And snooping would allow us to configure the one port on the switch that the DHCP server lives on. And if any other port on that switch provides a DHCP offer, the switch will simply discard that frame and will not forward it to anybody. So DHCP snooping will isolate the only authorized DHCP server to defend against the rogue DHCP server attack. In addition, the switch can also monitor each port, and if it sees multiple MAC addresses on a single port, it can be configured to deny additional DHCP requests. This will help us defend against the depletion of the available IP addresses on the DHCP server. So these are a handful of the attacks on DHCP and the new security that we can now add onto switches called DHCP snooping to help defend against these attacks on this vulnerable, unauthenticated protocol DHCP. We'll knock off here for a few minutes and we will pick up later with additional network services. Next, we're going to look at another networking infrastructure service called Domain Name System, or DNS. Now, as we've said before, DNS provides name resolution services. In other words, users are familiar with the friendly names of the infrastructure systems like webserver1.boboville.com or fileserver1.luluville.com, different names along these lines. These are called fully qualified domain names. However, in order to connect to these friendly named systems, the network stack must identify the IP address for that particular node. And that's where DNS comes in. DNS is basically a database that holds these mappings of these friendly names called fully qualified domain names, and it maps that fully qualified domain name to the IP address so that the network stack can actually use the network to transmit the frames back and forth. Now, the holder, the container, if you will, for these server names are called the DNS zone. And the namespace, like boboville.com, defines the zone name, and then the different local hosts, that would be like web server 1, file server 1, domain controller 1, these different local host names, then inside the boboville.com container, hold the mapping to the specific IP address. You can actually see this in the dialog box in the lower right-hand corner. We're looking at contoso.lan is the namespace, also called the DNS zone name is contoso.lan. That's on the left-hand side. It's highlighted in blue. And then inside that container are the actual mappings of the hosts, the actual server names, who are members of the contoso.lan namespace. And we see there's a DC1-2008R2. That's the local host name of a domain controller who is a member of the contoso.lan domain. And as you look to the right, you can see his IP address is mapped at 192.168.149.100. So there is that local host contoso.lan mapped to an IP address. That's a fully qualified domain name mapped to the IP address. That's what DNS does for us. And when a client needs to locate DC1-2008R2, that particular local host name, their client computer appends their domain name, contoso.lan, to that local host name, and then submits a query to port 53, the DNS server, and the DNS server searches its database in contoso.lan looking for the local host name that was requested, and will return the DNS response of the IP address that it has in its database, that it has mapped. So this is the name resolution process. Now, if a DNS server receives a query for a name he doesn't know, specifically a namespace he doesn't know, then that DNS server has the potential, if it's configured to do so, to ask an upstream DNS server. There are two different processes. These are called either forwarders, where we configure the server, if you don't know a name, go ask that DNS server, or the root hints. Now, the root hints are typically what's used when we get into the public namespace, out on the public internet. So internally, you'll very often use forwarders within your directory services environment because DNS is used for directory service support. And typically, you'll use forwarders internally and eventually forward out to a DNS server that has access to the root hints to support your client computers that are trying to browse the internet. And that's where we get our public namespaces that we would find out on the internet. When a DNS server forwards a query, either using the forwarders or the root hints, then if that server receives a response, he will cache that response typically for 60 minutes. This is referred to the time to live, TTL. It'll typically cache that response for 60 minutes so that it kind of memorizes that name to IP address mapping just in case somebody else requests that same information. And then it feeds that information, that mapping, back down to the client who requested that IP address mapping. Now, the client will also cache that information for the remainder of that TTL. As I had mentioned, DNS is a requirement of the X.500 directory services systems. Now, in implementation, directory services is most commonly implemented in Microsoft's Active Directory. The client computers that are members of an Active Directory domain must find a DNS server that has these service locator records, or SRV records, that are used to support directory services. So to support directory services, we must use DNS. The clients must be able to find that DNS server so that when they query for a domain controller to log into, if they can't get a hold of DNS, they can't log in, because that's the only way they know how to locate that domain controller is by looking for these SRV records for their namespace, like contoso.lan. Now, we've talked about internal DNS and external DNS. We need to provide internal DNS support for directory services support, and we need to provide external DNS, that's public DNS, for browsing of the internet. So your client computers need to be able to get to both systems, internal DNS and external DNS, private DNS and public DNS. However, we don't want to put our private DNS information out on the public DNS system, because this is too clear a mapping for the bad guys. This maps out our entire infrastructure for the bad guys. So we don't want to make this internal IP address mapping and name mapping. We don't want to make this available to the public internet. So we will split our DNS and keep a private DNS for internal use and directory services support. And I never want that information to show up in the public DNS zone data. And so we'll use two different DNS systems to support these two types of services, one for internal directory services and one for external browsing of the internet name resolution services. Now, the original domain name system was referred to as the Berkeley Internet Name Daemon, or BIND. This was introduced in 1988 and is primarily used in Unix and Linux systems. Currently, BIND is in version 9, and Microsoft also implements their version of this domain name system and simply calls it DNS. We'll knock off here and we'll take a closer look at the DNS architecture in our next lesson. In this lesson, we're going to analyze more closely the architecture that we would set up as an example for the DNS system, the domain name system. And this architecture we're going to look at supports both the internal private DNS namespace, keeping it secure and private, and also provides support for the public name resolution services. Again, an example, there are many different ways to set this up, but this tends to support all of the required components. So let's start by looking at the lower left-hand side of this. And in this example, we're going to be using the example from Microsoft's Active Directory, the implementation of directory services. And we're going to do this because the Microsoft Active Directory is the single most commonly deployed directory services environment. So we're going to use that as this example. Lower left-hand corner, what we see are the domain clients. These are the users in the enterprise networking environment. And typically we'll take multiple DNS servers deployed in the environment so that we have fault tolerance. We'll take about, in this example, since we have two DNS servers, we're going to take about half of our domain clients and point them to one of those DNS servers. In this case, on the left-hand side, we start with domain controller 2 or dc2.boboville.lan. Now, that's the fully qualified domain name for that domain controller that is also a DNS server. So in the Microsoft environment, you want your domain controllers to typically be DNS servers as well. And I'll take about half of my clients and point them to DC2 as their preferred DNS server. And just in case that server is offline for maintenance or some network interruption, we also give them an alternate DNS server service to query, and that would be dc1.boboville.lan, a second domain controller for this Active Directory environment. And then on the right-hand side of those, we see the other half of the domain clients that use the preferred DNS server for DC1 with an alternate pointing to DC2. This is for load balancing and fault tolerance. Just in case one of those domain controllers is down, all the clients can still get name resolution services and still find directory service support for their internal directory services requirements. Now, this is our private namespace, boboville.lan. And all the client computers will need to access that boboville.lan namespace to get this directory services support. But what happens when those clients want to browse the internet? We have to provide this support. So what we do is we point these DNS servers, DC1 and DC2, to another DNS server, a separate system, and this particular system does not support the directory services. It doesn't contain or hold any of the mappings that are used internally to support this directory services environment. So we will forward any queries we don't know to this caching-only server. So this server does not have any records mapped in its database. The only records it will ever have are when it forwards a query outbound to the public internet and receives a response, it will cache that in memory for whatever the remaining time to live is, the TTL is for that record. So that's why we call it a caching-only server. We make this system not a domain member because we want to isolate this communications server, this DNS caching-only server, from Active Directory because that's too sensitive information, and this box will regularly be communicating directly with systems on the internet. And I don't want those systems on the internet to be able to perhaps attack this box and gain any more information. So I'm putting this guy as kind of an isolation boundary between my private namespace, boboville.lan, and the public namespace that we find out on the public internet off to the right in this particular diagram. When a client queries, let's say DC1 for www.goodstuff.com, the boboville.lan name server, DC1, doesn't know that namespace. It doesn't have a record stored locally for www.goodstuff.com. So DC1 will forward that query to the DNS caching-only server. So that caching-only server is now called a forwarder. That caching-only server also doesn't hold any records, so he's going to forward that query out now to the public internet. And typically what I like to do is forward to my ISP's DNS server. I want him to do the work and send back only the response. I don't want to get involved in a querying process, an iterative querying process that goes back and forth. So what I'll do is I'll forward my query out to my ISP's DNS. Now that ISP, that's my internet service provider. That's the guy who provides me my internet connection for my enterprise. And typically they'll provide this service as part of your monthly subscription for connectivity to the internet. So I'll let his server do the work for me. And so I'll forward this same query out to that ISP DNS server. Now that server will have his root hints enabled, and that means he's going to do the iterative query process out on the public internet to identify the actual IP address for the server named www.goodstuff.com, the query that came from that client back in this private environment. So he's going to run to the root server, submit a query. That root server will point him to the .com server. The DNS server from the ISP is going to now go query the .com server for www.goodstuff.com. That .com server will send him back the IP address of the name server that is authoritative for goodstuff.com. Now, the ISP's DNS server will go query goodstuff.com name server and should receive the response for the www.goodstuff.com mapping. That ISP DNS server will now cache that response and then forward the response over to the DNS caching-only server for boboville.lan. That caching-only server will forward that response down to the dc1.boboville.lan, and that DNS server will forward the response down to the client. Now the client can connect directly to that www.goodstuff.com web server out on the public internet using the IP routing system. So that's how the public queries are supported through the use of forwarders and root hints to get our public namespace resolved. The boboville.lan name servers also provide the internal support for directory services. Now, all that said, we have to recognize that we're here at boboville.lan, but we have a boboville.com public service or namespace that we want to provide web servers, email service, perhaps FTP services. And so we'll have some public services in the DMZ, the demilitarized zone between the two firewalls. And so we want the public to be able to come to our systems and browse our internet so they can buy our stuff off our website We want to be able to have them send us emails, so we'll have a web server out there. So we need the public to be able to find our public services. And so what we'll have then is our public DNS service for boboville.com namespace. Notice the change in namespace now. Our public namespace is boboville.com versus our private namespace is boboville.lan. And so we'll now have a second zone for boboville.com that is stored in DNS and accessible by the users of the internet out in the public internet space, and they'll be able to query our DNS for boboville.com and resolve our www and our SMTP servers that are out there in that public namespace. Now, I would need that namespace to be very secure. So what I'll do is in my internal systems, dc1.boboville.lan and dc2.boboville.lan, I'll create a second namespace for boboville.com. And I will say that this is a non-dynamic DNS. In other words, it won't take dynamic registrations. And I will manually configure the mappings for www and for SMTP and for FTP and whatever other servers I want to put out there in that DMZ and provide public access. And what I'll do is I'll set this up as a primary DNS server for this boboville.com, my public namespace. And then the DNS servers out in the DMZ will be secondaries, which make them read-only so that the bad guys can't modify them easily. And now anytime I make a change, I will configure my internal server on DC1 and DC2. I'll configure them so that anytime I make a change to the boboville.com namespace, it will automatically go update those secondary servers out in the public DNS DMZ that hold that same boboville.com namespace. Now, those two DNS servers up in the DMZ will only ever hold that one zone, boboville.com. They will never hold information for boboville.lan. Why? Because those guys are going to be hammered on all the time by all the bad guys out there on the internet. So anything in that DMZ, I need to make them hardened and only put information out there that I want the internet and the bad guys to gain access to. So I only put my public zone out there and never my boboville.lan private zone out there. That's the split DNS. There's the architecture, very typical example of the DNS architecture that supports the split DNS for internal namespace support for your Active Directory services and public namespace support for users of the internet to gain access to your public web services. We'll quit here and pick up on other networking infrastructure services in our next lesson. Let's continue with a look at the DNS client side. That's the domain name system client side. Now, the DNS client is referred to as a resolver. That's a DNS client. So when I say the term resolver, that's the user who is trying to resolve a fully qualified domain name to the IP address so that the network stack can forward the network information, whatever it is, whether it's query or file transfer, whatever, to the appropriate system. Now, in order for that to happen, we have to get this name resolution to occur. If you look at the dialog on the right-hand side, towards the lower half of that, you see use the following DNS server addresses. We have a preferred DNS server and an alternate DNS server. So this is the client configuration. Actually, the dialog is for the basic IP version 4 configuration, and a core component of that is the bottom half, the DNS server address is preferred and alternate. And typically you'll want both of those populated because if you can't get name resolution, you are probably not going to be able to authenticate if you're in an enterprise environment, a corporate environment with directory services. And if you are perhaps using this at home, if you can't get access to name resolution services, you won't be able to browse the internet. So you must have DNS access in order to accomplish either of those things, support for directory services and also for browsing anything on the internet or connecting to servers on the internet. We must have connectivity, and that's why if we can't get to the preferred server, I provide the IP address of an alternate DNS server, and I'll query him only if that first server is unresponsive. Now, we query the DNS server when we're looking for this name resolution, as I've described, and When I receive a response back from the DNS server, the client will hold that response in memory in something called the resolver cache. That's a chunk of memory that's set aside just to memorize these name to IP address mappings. And there is a time to live stamp that comes along with that record. And whatever that time to live says, that's how long I will hold this mapping in memory, and then I'll discard it when that TTL counts down to 0. Now, in Microsoft environment, the default setting is typically 60 minutes for this time to live. However, that's very adjustable, and there might be times where you want to run that number way up or run that number way down. Keeping a very short TTL means the information will remain fresh. In other words, if somebody changes an IP address, I'll query more often, and that way I'll more quickly learn of the change of the IP address. Or if the environment is very static and those IP addresses don't change very often, I might run that TTL up to, let's say, 24 hours so that I'm not polluting my network environment with unnecessary DNS queries and responses. DNS is a very light-duty protocol, so it's not too heavy. But at the same time, if my environment is very static and these mappings aren't moving around very much, then perhaps I can live with a 24-hour TTL. And when the client holds this in memory in this resolver cache, he doesn't have to submit a query because he's already got the IP address memorized for webserve1.boboville.com, for example. And so there is no need for a query because I've already got that information memorized. So this is the resolver side, the client side of DNS. Now, there are some attacks with DNS because DNS is not authenticated. In other words, the users, the resolvers, are anonymous. And as a result, this lends itself to vulnerabilities. It might be a bad guy who's trying to interrupt or interfere with this name resolution process, because if he can destroy DNS, he can disable your ability to successfully authenticate in your directory services environment, and he can destroy your ability to browse the internet completely, or using something called DNS poisoning, he will overwrite mappings, a legitimate mapping. Let's say you want to go to www.microsoft.com. He can overwrite that mapping, legitimate mapping that would actually take you to Microsoft.com servers, and he can put in his IP address that is perhaps a bogus, spoofed Microsoft.com web server, only it's going to download malware, viruses, Trojan horses, things along these lines into your computer. So this is a very desirable and fairly common attack vector for the bad guys. So how does this work? Well, one approach is that the bad guy can break into, somehow compromise a DNS server through one of many different vulnerabilities that the server may have. And not necessarily breaking into the DNS system initially, he'll attack some other vulnerability on that server and then eventually gain access to the DNS system through privilege escalation and other forms of ancillary attacks. But at some point he gets to where he can alter the mappings in the DNS system, whether it's in its cache memory or whether it's actually in the database, depending on the nature of this server. And if he can overwrite a mapping or inject a new mapping to a bogus address, he now can redirect traffic to whatever system he wants. You're going to, let's say, google.com. Well, he can put in the IP address for his spoofed server for google.com, and instead of it being a legitimate search engine, it's now a web server that is going to pump down malware onto your system. The governments around the planet have recognized that if the bad guys break into the public DNS system, they could compromise all e-commerce on the internet. And this would be devastating to the global economies, the global economy singular, and the individual nations that make up that global economy. Their economies could be destroyed as well. So this is a huge vulnerability and a huge threat to global economy. So the proposed solution is called DNSSEC, DNS security. And the point here is that if a bad guy had the ability to break in and overwrite these mappings, or could perhaps send bogus responses. So you are a resolver, you send a query for www.google.com, if a bad guy could inject a malicious or unsolicited response for www.google.com, only instead of it being a legitimate mapping, he points to the IP address of his bad guy server. That would be the way he'd compromise the systems. What DNSSEC proposes is that all these DNS responses will be digitally signed, and you, the resolver, would validate the digital signature on that DNS response. So this would imply that the response came from a legitimate DNS server, not the bad guy injecting a response, and that the response hasn't been altered. That's yet another attack vector that the bad guy could implement, and he would capture, as man in the middle, he would capture the legitimate DNS response, alter the DNS response by manipulating the IP address pointing to his bad guy web server, and then forward that response on to the client. So DNSSEC would prove authentic DNS server response and that the response hasn't been tampered with or hasn't been altered. The integrity of the responses is still high. So DNSSEC is the proposed solution, security solution for some of the major attacks on DNS. It's being slowly rolled out now across the globe. There are some weaknesses in it. However, at this point in time, it's the best we have. It hopefully will improve as it gets deployed and ages. We'll take a break here and we'll pick up shortly.